Okay, so for today's video, we're going to cover our first non-hydrocarbon functional group. We are going to cover alcohols. So an alcohol is where we have an OH group, a hydroxy group, attached to an alkane type carbon. And our parent chain is going to be the longest carbon chain carrying the OH. We're going to start numbering our chain at the end nearest the OH, and we're going to name our molecule by taking the alkane name, dropping the E, and replacing it with OL. And if our parent chain has more than 2 carbons, we're going to have to give a position for the hydroxy group. Okay, so go ahead and pause the video and see if you can give me a name for each of these molecules on this slide. Okay, so let's start with the one at top. We'll start by numbering our carbon chain. And so a 2-carbon alkane would be ethane. We're going to drop the E and add OL. So the IUPAC name for this molecule would be ethanol. Okay, let's try the one at the bottom. So we'll start by numbering our carbon chain. So a 7-carbon alkane would be heptane. We're going to drop the E and replace it with OL. And since this chain is longer than 2 carbons, we need to give a position for our OH group. Our OH group is at position 3. So this molecule would be 3-heptanol. Okay, so one thing you're going to have to do in this class is classify carbon atoms and alcohols by degree. So the degree for carbon atoms is going to be equal to the number of carbon atoms attached to that carbon, directly attached to that carbon. And we're going to use a similar strategy for alcohols. The degree for an alcohol is going to be equal to the number of carbon atoms attached directly to the hydroxy carrying carbon. Okay, let's try some examples. So for each of these, I want you to give me a name and then the degree. So go ahead and pause the video, see if you can come up with an IUPAC name and a degree for each of these alcohols. Okay, so let's start with the top one. So we'll start by numbering our chain. So a 4-carbon alkane would be butane. We're going to drop the E and replace it with OL. And since the chain is greater than 2 carbons, we have to give a position for our hydroxy group. And it looks like our hydroxy group is at position 1. So that means the final IUPAC name for this molecule is 1-butanol. Okay, so take a look at your hydroxy carrying carbon. How many carbons are directly attached to the hydroxy carrying carbon? We only have 1 carbon attached to our hydroxy carrying carbon, so this would be a primary alcohol. Okay, let's try the middle molecule. So let's go ahead and number our parent chain. So a 3-carbon alkane would be propane. We're going to drop the E and replace it with OL. We need to give a position for our hydroxy group. It looks like it's at position 2. But we also have a substituent at position 2. It looks like we have a methyl group at position 2. So that means our final IUPAC name for this molecule is 2-methyl-2-propanol. Okay, so let's take a look at our hydroxy carrying carbon. It looks like it has 3 carbons directly attached to it. So that means this would be a tertiary alcohol. Okay, so let's go ahead and try the bottom example. So we'll start by numbering our parent chain. So a 4-carbon alkane would be butane. We're going to drop the E and replace it with OL. And we need to give a position for our hydroxy group. And it looks like our hydroxy group is at position 2. So the final IUPAC name for this molecule would be 2-butanol. Okay, so let's take a look at our hydroxy carrying carbon. It looks like there are 2 other carbons directly attached to it. So that means this is a secondary alcohol. Okay, so our next functional group we're going to talk about are phenols. So a phenol is an aromatic organic compound consisting of a hydroxy group attached to a benzene ring. So why do we differentiate alcohols and phenols? Why can't we just consider phenol an alcohol? Well, it's because they have very different chemistry. So phenols, as you'll learn in the next module, can act as weak organic acids. They can actually donate this proton here. Alcohols, however, can't do that. The H attached to an alcohol is not acidic. So that's why we distinguish between alcohols and phenols. So how do we name phenols? So the parent chain name is going to be phenol. We're going to begin numbering on the aromatic ring at the carbon atom carrying the hydroxy group. So let's try one. So go ahead and pause this video and see if you can come up with an IUPAC name for this molecule on the right. Okay, so let's start by numbering our chain, and we have to start with the hydroxy carrying carbon. So it looks like we have a methyl group attached at position 4. So that means the full IUPAC name for this molecule would be 4-methyl-phenol. Okay, so what we actually drew in this last slide is a molecule called cresol. So cresol is the common name for any methyl phenol. So using the OMP nomenclature that you learned about in the last video, go ahead and pause the video and see if you can tell me what another name could be for 4-methylphenol, 3-methylphenol, and 2-methylphenol. Okay, so using the common name of cresol and the OMP nomenclature that you learned about in the previous video, another name for 4-methylphenol would be paracresol. 3-methylphenol would be metacresol. And 2-methylphenol would be orthocresol. Okay, so let's talk a little bit about physical properties. So what is the strongest intermolecular force that can occur between two phenols? So go ahead and pause this video, draw a pair of phenols, and connect them with the strongest intermolecular force you can. Okay, so let's draw our first phenol, and let's look at our table of non-covalent forces. So the strongest is the ionic bond, but we can't have an ionic bond between two phenols because there's no ions here. There's no charges. So we can go and cross that off. Can we make a hydrogen bond between a pair of phenols? So a hydrogen bond requires both a hydrogen bond donor and a hydrogen bond acceptor. And a phenol can act as either a donor or an acceptor, so we can definitely draw a hydrogen bond between two phenols. So that means the strongest non-covalent interaction that can occur between two phenols would be a hydrogen bond. Okay, so what can we say about phenols and water solubility? Well, phenols can hydrogen bond with each other, then that means they would have no problem hydrogen bonding with water either. So given this, you would expect phenols to be fairly water soluble, right? Well, they're actually only slightly water soluble. So while they can make this really strong hydrogen bond interaction with water, they have these big, bulky aromatic rings that are completely nonpolar and can't interact with water at all. So what ends up happening is phenols tend to be slightly soluble. The OHs can interact really well with the water, but these aromatic rings prefer to clump together.